All right. So in the previous video, I showed you how to take your Skynet data and make two HR diagrams, one a little bit more towards the blue, one a little bit more towards the red, and we matched isochrones to your Skynet data, dating the cluster, measuring its metallicity, measuring the amount of reddening due to dust between us and the cluster. And the idea is you're doing three clusters: a young open cluster, an intermediate open cluster, intermediate age, and an old globular cluster. And everyone in the group should match the isochrones to all three clusters. And then in the module, there's a link to this page where here you have the open cluster, and each teammate puts down their measurement of the distance, the age, the metallicity, and the reddening. So each teammate lists it, and then it will come up with the average for the team and the standard deviation. And that gives you some idea of the uncertainty. When you're doing this just by yourself, you don't really know, what are my error bars? How accurately am I doing this? How accurately am I measuring these parameters? So the idea is everyone in the team will do this for all three clusters, and the scatter between the teammates gives you an idea of how accurately this can be done. In this case, just using the Skynet data. Now, once you've done this, we can improve upon it by adding in some archival data. Okay. So I'm going to show you how to do that. And I'm going to show it using an old globular cluster. This one right here. In the last video, I did an open cluster. And the open clusters that we observe are all pretty close to us. And so, the stars are brighter and we can see farther down on the main sequence. The globular clusters are using just the Skynet data can be pretty challenging. They're very far away, and so we don't see the faint end. It makes it challenging to match the isochrone to the data. You'll have probably the greatest scatter, the greatest uncertainty amongst your teammates with your globular cluster. But once we add in this archival data, that will help tremendously. Okay, so this is 47 Tuck. It's this globular cluster. Okay, I've already loaded in the Skynet data. So here we are on the field star removal page. And with open clusters, as we saw last time, most of the stars in your image are unrelated. They're field stars. Only a small fraction, 30% in that particular example, were cluster members. Globular clusters are different. With globs, almost every star in the image is a cluster member. There are some unrelated foreground stars that just happen to be there, and we do want to remove them, but it's pretty easy. Again, most of the stars are cluster members, so they all have the same motion across the sky. They're all moving together, so you get a big clump in proper motion space. I've just zeroed in on it a little bit. Distance here, it's at a distance of about 4.85 kiloparsecs. Remember, you got to make note of that because we're going to use that number later on. And again, we can check here. You can hover over the term field stars, make sure that you didn't cut too much. This looks to be fairly uniform, so this is a good field star removal. One thing you may want to do at this point is come up here to the triple bar and download it as a PNG or a JPEG so you can make use of this proper motion cut in your blog. Okay. Anyway, once you're done here, you proceed to fetch archive. And then you proceed to isochrone matching. And I've already matched the isochrones to the Skynet data. Here we have our bluish HR diagram and our reddish HR diagram with the Skynet data. And the first thing you have to remember to do is to enter that distance from the field star removal page. I think I said 4.85 here. I got 4.8 before, so I'll just run with that. And with globs, they're quite old. And so the age, in this case, I had to take it all the way to the maximum. Metallicity with globs, they tend to be on the lower side. With opens, they tend to be on the higher side. And in this case, not much dust between us and the line of sight. And it looks by eye to be pretty decent. What makes these hard is since they're so far away, we're not seeing the faint end, and so we don't really have good data at the turnoff point. And that turnoff point is the most useful way to measure the age of the cluster. What we do have is the horizontal branch. Getting this little purple bar, that's where you have the helium core burning going on. You can use that to get a decent approximation of the age. But it's tough. Without those faint stars, it's tough. Just do the best you can. Okay. Now, to improve it, we're going to add archival data. So we go back to archive fetching, add catalog stars. The catalogs we want are Gaia and 2MASS. Okay. And first, you're going to test the radius. Now, with most open clusters, the default radius here is just fine. But with globular clusters, since there's so many stars there, you can see it says too many stars, reduce radius and try again. If we load too many stars into your browser, it gets too sluggish. So we cut it off at 5,000. Here, I'll drop it all the way to 0.1 degree search radius. Test the radius. Still too many stars. This star cluster has a lot of stars. Let's try 0.05. Test radius. Okay, this one worked, 2858 stars. Let's increase it a little bit, see if we can get a few more stars. 4634. Increase it a bit. Too many. Okay. So 0.06. I'm going to fetch that data. Takes a moment. Okay, it's found it. So now it's just going to prep it and transfer it. Here we go. Okay. Now that box will disappear, and just wait a second. It's updating these this bar graph. Okay. So here under user, after we made our cuts, we're down to 2769 cluster stars. To that, we added from Gaia 4506 cluster stars. Now, Gaia is going to be really useful for detecting fainter stars. The telescope is about the same size as our telescopes on Skynet, but it's in space. So it can see fainter, it's going to see farther down the main sequence, it's going to let us see that turnoff point. Now with 2MASS, it's over here, just adding 229 stars. 2MASS is a near-infrared survey. And from the ground, two telescopes, one in the south, one in the north. The one in the south is actually right next to the prompt telescopes at Cerro Tololo in Chile. This is useful because in the near-infrared, excuse me, dust does not have as big of an effect. And so by combining near-infrared data and optical data, that should make it a bit easier for us to constrain EB minus V. Okay. So we're going to proceed to isochrone matching. Okay. Now, let's add in these two new data sets. For Gaia, it has a blue passband, BP. It has a red passband, RP. And then G is just kind of like a combination of the two. We'll put that on the luminosity axis. Let's add that. There it is. And for 2-mass, the filters are JHK. J is the blue one. K is the red one. H is in the middle. We'll put that on the luminosity axis. Add that. Okay. Now, maybe a little hard to see. Everything's kind of squished. The dots are kind of big. Couple tricks here that you can do. First, you could try frame on data. And that works usually really well for the archival ones. We could try it with the Skynet data, but at the faint end, we have a lot of scatter. Let me move this bar all the way out here. And because of that scatter, it causes, the interesting part of the data set to get squished. Now, you can get rid of some of that. A lot of the scatter, they have large error bars. So if I decrease the max error, I can get rid of some of these here. See, I did that, and then the graph rescales and expands. Adjust it just a little bit more. Okay, that's good enough. So, that's one thing you can do. Another thing you can do is on a PC, hit Control minus a couple times, or on a Mac, Command minus. And so this makes everything smaller, all the text, all the boxes smaller, and gives you more room for the graphs. Now, when you do this, just a little bug that we'll hopefully fix soon, you're going to have to type the distance back in. I think we're using 4.8. Okay. So now these are relatively bigger and the dots are a little bit smaller, and it makes it easier for you to see what you're fitting to. And looking at this here, here's the Gaia data, and it does make it all the way down to the turnoff point. So we can adjust. Now, I can't make it any older because I'm already at the maximum, but I can change the metallicity. Try that a little bit. Let's pop that back a little. And you can do fine adjustments here as well. And that's pretty good. That's pretty good. That fits this well. It didn't mess up the Skynet data too much. Often when you have all these different data sets with different filters and calibrations, it's impossible to get them all to fit perfectly. You kind of have to come up with the best solution for all of them put together. Some may be a little bit redward of the line, some may be a little bit blueward. Just try to come up with the best overall solution. Again, when you're doing these matches, you want to take your time. And when you're done, come back to this sheet. Now go to the second tab, and you're going to input your improved values. Improved now that you have the archival leverage, Gaia and 2-mass to come to a better solution. Again, every teammate should do every cluster. So you'll be filling all this in, and you'll have a team average and a team standard deviation. And hopefully the values got more consistent. The standard deviation hopefully went down once you added in the archival data. Okay. Oh, and lastly, come back here and hit the 3 bars and save your plots. Your Skynet plots, and also your Gaia and 2-mass plots, because you may want to use them in your blog. All right, that's it for this video.